Okay, I can't believe it, but we are on the last day of 12 classes, and I think no other better way to end 12 classes on a channel called RandomMathsInc than to talk about a mathematics class. And the class I'm going to be talking about today is a class called Real Analysis. So this one should be fun, so let's get right into it. So real analysis, what exactly is real analysis? As the name suggests, real analysis studies about, well, real numbers, which is usually denoted by a letter R, or a more fancy R, sort of like that. And in real analysis, we deal with real numbers, and real numbers are basically just, well, numbers that you see, like usually in daily life. So numbers like, for example, 1, or 2, or numbers like pi, or even something like minus 4.286, or something irrational like pi, or maybe even something like square root 2, or something like that. Those are all real numbers. And these real numbers, you can sort of say, they belong on a real number line. So real number line might have number 0 right in the middle, then you'll have 1, 2, 3, and so on. Then also it goes into the negative direction, things like that as well. So in real analysis, you talk about all of these different numbers and how they can relate to each other and things like that. So if you guys have studied classes like Calculus 1 or Calculus 2 before, then you probably have seen a lot of the concepts like functions and sequences, and whether a function is continuous at a certain point, or whether a sequence converges to a certain number, things like that. And in calculus, or in lower level calculus classes, you look at these numbers and basically, you know, their definitions, or for example, definition of a sequence converging to a certain number, you can just sort of think of it as, you know, like it converges because we can see that numbers get smaller and smaller, and it sort of approaches this certain number. So you can sort of use your feelings to say that a sequence converges, but often, you know, like that's not really good enough for proof. So for example, if you want to know about convergence of a sequence, like maybe there is a good way to characterize what it means for a sequence to converge rather than just using your feelings. Give something concrete, a more concrete definition to some of these concepts that you've seen before. And, you know, like, so eventually you can see that a lot of the concepts that you have already seen in previous calculus classes can be defined a lot more rigorously, and have like sort of like a really fixed definition, basically saying that this is only true if this condition applies. And, you know, it sort of takes out the whole intuition part, or the whole part that you have to sort of guess around with the limit sort of thing to it. I mean, you still have to guess the limits, but if you want to show that the limit is true, or whether a sequence converges, things like that, there is a more clear way to show that it must be the case, using a more rigorous definition and not having to rely on, like, you know, feeling like it must be true, and so it probably should be true, and things like that. And so, you know, given that some of these concepts you might have seen already before, how would you cover these sorts of concepts in a real analysis class? So, firstly, in like maybe the first few weeks, or, you know, first few sections, you can talk about something called sets and sequences of these real numbers. Well, first of all, what is a set? A set simply is just, well, a group of numbers, right? So for example, you might have a set like this. This one is a set of numbers. You might have a set maybe like of 1, 4, -2, for example. That is a set of real numbers, maybe 2.3, just to make it more interesting. But you can also have other sets which are infinite. This is a finite set. You can have infinite sets. So for example, you can have a set of natural numbers. This would be numbers like 1, 2, 3, and so on. Or you can have a set which is, you know, for example, a set like all the numbers between 3 and 5, right? So you can have a set of all the numbers such that it is between 3 and 5 exclusive, not including 3 and 5 itself. Sometimes also denoted by this, I'm not sure if this is actually the correct notation for it, but yeah. You can also have something that actually includes the endpoint. So for example, maybe from -2 to 0, something like that, usually denoted by that. This is what we call an open interval, this is what we call a closed interval, and as you can see, it's still a set of numbers. But I mean, if you have a set of numbers, what other things can you say about it? Well, for example, you can say, if you have a set of numbers, these set of numbers that all we've shown here, except for this one, all of these are actually bounded sets of numbers. You can talk about the maximum and the minimum of these sets of numbers. So for example, I can take this one and I can, let me just, for example, draw a number line like that. Then this set, this set here, you can sort of draw it out like so. So it will be a 3, there is a 5, and you can use these brackets to denote that I'm not including 3 and 5. And basically this set covers all of these different numbers here, right? So as you can see, 5 here could be a maximum of our set because all the numbers is less than 5. But then also a number like 6 can also be a maximum of our set because all the numbers is still less than 6. So all of these numbers here is a maximum to this number, or not a maximum actually, it's called an upper bound. I was using the wrong terminology there. All of these numbers here from 5 onwards is all an upper bound of our sets. Things like that. So you can, for example, define things like upper bound, you can define things like a lower bound, and there's such thing as a lowest upper bound. So all of these numbers is an upper bound, but this one, this number 5 here, is sort of the tightest upper bound. So formally this is called the lowest upper bound because it's an upper bound and it's lower than all of the upper bound, also called a supremum. Then, for example, what properties of this do you have? So it turns out that, for example, all the sets which are bounded, so this is a bounded set because it doesn't go all the way to infinity, all bounded set has got a supremum. That turns out to be a very important concept in real analysis. It seems like a really obvious thing, and in fact it is really obvious, but it's so important that it has a special name called the axiom of completeness. And the reason it's called an axiom, it's because, it's basically the starting point for real analysis. If you do real analysis, this axiom, the fact that all bounded sets has got a supremum, has got a lowest upper bound, this is basically the starting point to real analysis. It seems like a really small fact, but eventually from here you can lead on and do a lot of crazy stuff with it. And as I mentioned in some of the earlier videos, I think I might have mentioned once in classical mechanics that basically if you want to be able to build on to other concepts, you have to have a starting point, and this turns out to be a starting point for our discussion of real analysis. Now we have the ideas of sets, we have the ideas of upper bounds and lower bounds of a set. What other things can we have? Well, for example, now we can talk about things like open sets and closed sets. So you might have heard of the word open sets and closed sets before. This turns out to be an open set, this turns out to be a closed set. One idea of an open set that you can have is a set where you're not including like the endpoints. So that's one example of an open set, but how do you make that more rigorous? And a closed set intuitively should include the endpoints, right? So for example, like this, if I don't include the 3 and the 5, this is an example of an open set. It's not the only open set out there, but it is an example of an open set. But if I have a set which includes the endpoints, so this set includes 3 and a 5, turns out this is a closed set because it sort of includes the endpoints. It's not the only example of a closed set, but it happens that this is a closed set as well. And for now, you sort of think about it very intuitively, like saying, oh, it includes the endpoints, so it's open. But how do you give more rigorous definitions to that? In real analysis, there are more rigorous definitions to it, which I won't go through in this video because I don't think we should. But basically, as I've mentioned, real analysis is all about giving rigor. So open, closed, how to make it more rigorous, right? That is basically like what this class is about. This is sets. so far, we can also talk about sequences, as I've mentioned. So you might have seen sequences before. So for example, an example of a sequence would be something like 1, 1/2, 1/4, 1/8. This is a sequence of real numbers. How can we define sequences, in the context of this class? Or how can we define it maybe a bit more rigorously? Well, not really rigorous, but like a more concrete definition of it. Well, you can look at a sequence more as a mapping. So for example, I can label all of these numbers, right? So I can say this is the first number, second number, third number, fourth number, and so on. So I can say that, a sequence is basically a mapping going from a natural number to any real number, right? So you can have a natural number and then you can map that to any real number. So looking like this sequence has got infinitely many terms, right? And basically I can ask, give me a natural number, and I can give you a number in that sequence, right? So first natural number corresponds to number 1 in the sequence. Second natural number, number 2, corresponds to 1/2, things like that. Now, you might have seen a lot of things about the sequences before. So for example, this sequence, it turns out that a of n, this tends to 0. But why does it tend to 0? How do we even know that a sequence like this one will actually converge to a number? So you have the ideas of, for example, convergence. When does, a sequence converge? Or how do we know about the limit of, our sequence even? So there are ways we can rigorously define that. So just because I have, because I can do it. Suppose you have a number line. I know that the numbers will tend to 0 for this case. So this is 1, this is 1/2, this is 1/4, this is 1/8, right? For example, this is the first number, second number, third number, fourth number, and so on. And as you can see, the numbers will actually tend towards, it will actually tend towards 0. Well, there's many ways we can see how, a sequence like this converges. Well, first of all, we can see that as we get closer and closer, as this number, as the index goes up and up, the numbers gets closer and closer to 0. So what we can really define is we can say that maybe, for example, if I draw a bound around 0, maybe something like that. You can't even see that, can you? If I draw a bound between 0 like that, which can be as small as you want, right? This can be as small as you want. Call this epsilon. Right? Then that means that you can always fit all the numbers a of some n, and then a of n plus 1, a of n plus 2, and so on. All of these numbers can all fit between here, right? So this is a very complicated definition. It looks really complicated, but basically what it's saying is that, all the numbers, if you have, for example, a box around 0 of a certain size, then all the numbers might start outside. But eventually, all the sequences will eventually become inside of the box, and then it will stay inside of the box. So, A4 right now outside the box, A5 might be inside the box, A6 will remain inside, A7 will remain inside, and the sequence will all remain inside. And I can choose this epsilon, this size of the box, to be as big as you want, and you can always tell me when the numbers starts getting into the box and never leaves again, or which term in the sequence will the number remain in the box and never leave again, right? So this is basically the more rigorous way to define convergence of our sequence, and actually defining the limits of our sequence. So this actually has got, you can write it out rigorously, which I won't bother, but this is basically the idea of convergence. So any sequence where you can do this, where you can, for any box, you can give, a term which all the numbers will remain in the box, things like that, then it converges to a certain limit, to a certain point. But then you can also, for example, tell other things about, about the limit. So for example, if you know that your sequence is all decreasing, which in this case it is all decreasing, and you can fit all of your terms inside some set, which I believe it has to be a closed set. I can't remember if it's a closed set or an open set, but basically if all your terms is monotone, or basically all increasing or all decreasing, all fits inside a set, all fits inside one box like this, then it's also a convergent series, things like that. But basically that's the ideas of a sequence. So you can study sequences of numbers. You can ask things like, what's the limit of a sequence of numbers that you have? Things like that. And as I mentioned, have a more concrete definition of what these things are. Because convergence, I mean, you probably know that this converges to 0, right? Like just by looking at the numbers, because all the numbers get smaller and smaller and smaller. So obviously it has to go towards 0, but how can I show it that it definitely has to go to 0 in a more concrete manner, right? And then once you actually talk about sets and sequences, you can then start to talk about something that's actually a lot more interesting. And these are what we call functions. Well, first question you may ask though is, what exactly is a function? Well, you might have seen functions before. I think functions is something that a lot of people probably seen before. So for example, f of x equals to x squared. That's a function. And basically what this basically means that you can put x to be anything in here, and to get the value of that function at x, you just square it, right? X can basically be any number in the real set, or any real number. So basically what this function does, what a function really does, is it takes a real number and then it maps it on to another real number. For example, if x equals 2, 2 is a real number. If I put 2 in that function, you get out 4. And 4 is basically another real number. So it basically sends one real number to another real number. You can sort of write it out like this, right? X and f of x. It basically sends one number to another number, right? Like 2 to 4, or 3 to 9, and maybe, for example, minus 3 to 9 as well. But as you can see, this set is a real number, and this set is also a real number. You can compare this to a sequence. So maybe, for example, an is equals to something, right? Maybe concreteness 1 over that, right? This is something very similar, but rather than mapping a real number to another real number, it only maps a natural number to a real number. You can think of it that way, right? So for example, 1 will get mapped to 1/2, right? 2 will get mapped to 1/4. But you can't really map things like, for example, 3.5. There is no 3.5 term in a sequence. So you can sort of compare that functions and sequences are something that is sort of similar in a way, because it is a mapping between, something to something else, right? Real numbers, real number to real number, sequences, natural number to real number. So you can graph a function like that. I'll actually use a red pen here. So, for example, it looks like that, a parabola, right? As you've seen before. But, functions, similar to how, sets, we have a limit for a set, basically which number it converges to, we can ask something very similar to a function. Like a function converging to a number, that's basically a limit. So maybe I can pick a point like there, like x equals to 2, and I can say that, the limit of this function as x approaches 2, right? So you might have seen that before. So notation is like limit of x approaching 2 of x squared. I mean, obviously this example is really easy. You know that it must be 4, right? But how can we prove that it is 4? Like, how can we show this rigorously? Because for much of calculus that you've been studied, like, this just feels obvious. Like, why do you know? Because, you can go closer and closer to this point, closer and closer to this point, and you know that your number must approach 4, right? You just know by intuition. But in mathematics, intuition is not really good enough. And the reason is because, well, you can't really prove stuff with intuition, right? I mean, yeah, sure, you can pretty much just write this down and everybody sort of knows that this is true, but how can I, make this concrete, make this definition concrete? Well, we can use the ideas of you getting closer and closer to the number, right? So, for example, let's do this. So I'm going to use a very similar idea to the convergence, where we're drawing boxes around the numbers. So suppose on the y-axis, I can draw a box, right? I can draw a box of some certain size around this point 4. If I think 4 is, for example, the limit of this at x equals to 2, I can draw a box around 4, right? The box will, again, we'll just say it's some certain size epsilon. Now in the convergence example, we can see that eventually if we set this box to a certain size, we know that there must be a term that starts to remain in the box and never leaves it. So it's a very similar idea we can have here. So, if we have, an epsilon, a certain size of a box of this size, like this, then we know that there must be some certain values of x, which is around x equals to 2, which, all its values remains within this box, right? Remains within this box and never leaves it. So for example, here might be maybe, for example, like 1.9 and 2.1. I think this is definitely not going to be the values, but just as a concrete example. So we know that all of the numbers between these two will be, all its values of f of x will be within this box that we came up with. Right, so I can make this box even smaller. So maybe, for example, if I make this box even smaller, right, I'm gonna redraw this axis out here, something like that, yada yada yada, a line like that. So again, at x equals to 2, right, this is 4. I can make a box even smaller, like just covering 4, like that, and we can still find a box around this point of x where all the numbers there will be within this box there, right? And so it turns out that it doesn't matter how small our epsilon is, how small we squeeze this box to be, I can always find a box on the x-axis, or a number between, a set of numbers covering our point x equals to 2, where all of these numbers, when passed into the function, will still be between epsilon, right? So I can write this out more rigorously. So this is true if I can find some box. If, for example, I have some epsilon, I can find a set of numbers, a box covering these numbers. So I can find some, maybe a set, some delta, I'm going to call it delta, where all of the numbers, so for this case, we're going to say 2 minus delta between x and 2 plus delta. So talking about this set here, we can find such delta, or find such a box here, such that f of 2 minus epsilon will be between f of x, f of 2 plus epsilon. Right? So basically what this is saying is that for every epsilon that we have, any size of this box, we can always find a delta. There exists a delta, or we can find this box of any size, such that if we have an x within this box, then f of that x will be within this box. And this is a more rigorous definition of a limit. Obviously, I've written it out a little bit messy here, but the idea is basically just that this is what we call the delta epsilon definition of a limit. The reason we call it delta epsilon is because of the delta and epsilon there. And it's a more rigorous definition of a limit. It basically takes an idea that you sort of already know, that, as a number gets closer and closer to x equals to 2, the value of the function gets closer and closer to the number of 4. And that's a rigorous, that's an intuitive definition, but how can we write that out as a rigorous definition? The answer is just delta epsilon proofs. And now that you have a good definition of a limit, you can go wild with these sorts of things. So for example, you can now define the concept of continuity, right? What is a continuity of a function? Well, for example, if you have a function, something looking like this, right? Then you can define the function being continuous at a certain point, right? So there's a couple of definitions. One is that, the function exists at that point. Two is that its limits exist at that point, and we know that the limit exists if we can find, like that number. And also that the function we evaluate and the limit at that point is also the same. So that's the idea of continuity. You might have seen that in like lower level calculus classes, maybe calculus 1, things like that. But the idea of continuity is basically the same. The only change now is that we have a good definition of a limit, right? So for example, like x equals to a, that would be f of a. This function is continuous if f of a exists if limit of x approaching a of f of x exists, and these two are basically the same three things. That basically defines continuity. But then you can also go, a lot more wild. So there's loads of other theorems, things like intermediate value theorem, things like Rolle's theorem, things like that, which I won't go through in this with this context. But then you can also go into more interesting things. So for example, the derivative, because now that we have a definition of a limit, the derivative is just really easy to talk about, right? So for example, you can talk about like what is a limit, right? Definition of a limit is that, I think. So I think it was something like f of x minus f of a, x minus a. But now you have a definition of a limit. You have a more rigorous way of defining a limit, which means that this has got a more rigorous definition, so you can do more things with it. So things like L'Hopital's rule, which I think some of you might have seen before. Turns out this is actually, you can only prove this if you know like a more rigorous definition of limit, which is this one. You can prove other things as well. So there's things like power series and Taylor series, which require the derivative, which I sort of mentioned in I think my numerical methods video. But yeah, basically that. You can talk about the integral, right? The integral. Most people will probably have studied the Riemann integral, which is where you draw like boxes around underneath the function, underneath the graph, and then say like what's the area of that box. There is a more rigorous way we can define the integral, which I won't get into here, but it's basically drawing boxes something like this as well. But then there is like a sort of biggest box that you can draw and the smallest box that you can draw, right? So if I have a line like that, the biggest box I can draw might look something like this, right? If I divide all of these equally, the biggest box I might be able to draw might look something like that, whereas the smallest box I can draw will only look something like that, right? This is the smallest box, the pink one is the biggest box. But then as you make this box finer and finer, the area of the biggest box you can draw and the smallest boxes you can draw, the areas that you add up eventually becomes smaller and smaller and becomes closer and closer together. And if it actually eventually goes to the same number, it means that you can have an integral, the integral exists. Basically that's what an integral is. You can also see that derivative and integral are actually both connected to each other through something called the fundamental theorem of calculus, and you can also show that that is definitely the case. But basically that all is available to you once you get the limit definition of a function, which again will be related to things that we have talked about before, things like sets and sequences. But basically that is real analysis, just dealing with natural numbers and what sort of things can you go on to talk about once you have all these fundamentals of natural numbers, not natural numbers, real numbers locked in. And so as you can see, some of these words that you've seen here that I've mentioned, things like sets and sequences and limits and continuity and things like that, these are all words that you have probably already seen before in a lower level calculus class, and you might have sort of an idea of like what they are, or at least what they are intuitively. But it's much better to have it written out as a more rigorous definition, and I haven't really done that. I haven't really written out a more rigorous definition, but at least like it should point you towards like a more rigorous definition of how mathematicians will actually define some of these concepts. And having a rigorous definition of these concepts, as I've mentioned, is very helpful into taking some of these ideas that you already know and then sort of using it to prove other things, because now you don't have to rely on feelings. You have a very concrete definition that people agree on of what this certain concept is. And some of these concepts seems really abstract, and some people might think like, where do I even use this in real life? Things like that. And one of my teachers, not my real analysis teacher, summarizes very well that real analysis is like going to the gym, that you just sort of exercising your brain, and like your mental mind gets stronger, you become a better person, better mathematician, write better proofs, more capable of doing things mathematically. But like maybe there isn't really that much use in real life, but it's still a very interesting class, and I still would encourage people to take it because of how interesting it is, and I think there is a beauty in being able to take an idea that you have, or an idea that you might have a good intuition of, or like a good picture of, and be able to drill down and write down a very concrete definition of what it is. And I think a lot of real analysis basically just does that with a lot of the definitions that you've seen, things like that. And yeah, it's probably the most rigorous class that I've taken like in my university, like ever, because of like how much definitions there are. There are also loads of homework. The homework is just basically like loads of proofs and like saying that, you know, prove this statement, things like that. Like you hardly see any numbers. Sure, we talk about real numbers, but once the homework comes out, you hardly see any numbers. It's just prove this statement using things we have learned in class, or using things that we have proved in the past. And proofs are really long. I'm not sure, I might stick an image of like a proof I wrote. It's probably like some proofs goes up to like a page or two or something like that. It's a really fun class though, but it's also really hard, and it's a real mind twister, I would say. But yeah, that's basically it for real analysis. I think you know, you probably are a bit more familiar with what it is now, and actually that is it for actually this entire series of 12 classes. I've talked about 12 classes that I really enjoyed. The classes are also very different. You have some classes which is more theoretical and more more analysis, classes like analysis where it's more rigorous, more theoretical. But then you also have classes which is a lot more like sort of more practical that I mentioned. The classes come in different styles. Some is really heavy mathematics, some is just using mathematics. It's really fun. There's loads of different things I've learned in the past 3 and a bit years. Almost graduated, thank God. Really, all the videos I've made, all of them is, you know, maybe about 10 to 20 minutes. And I sort of wanted to give a good introduction to some of those different topics. I realized that some of them maybe wasn't as good as as it could have been, partially because of time constraints. All of these 12 videos was made in a space of about like 2 weeks, and some of these videos I'll probably look back and cringe at myself, things like that. But I think like at the very least I gave some good basics of what some of these classes are, and I can't do justice in a 20-minute video about any of these classes. Like I probably need at least an hour or two to talk about everything in these classes, or at least even some of the more important stuff in these classes. Maybe some of you might enjoy that, and maybe some of these classes might become a standalone video in the future where I just talk about like the concepts in the classes and stuff like that. Because there's loads of video idea that I do have, just not the time. And some of the video ideas that I have, and some of the videos that you have seen recently, have been taken from some of these classes. And but anyways, yeah, I think that's it for this series. Thank you very much for all the support that you've given me in the past 12 days, and actually ever. Some people might be new subscribers here. This channel is now about 6 years old. No, maybe 7 years old actually. But some of you guys have just joined. It's still great anyways. Thank you very much for that. Thank you for 5k subs. Might make a special on that, I don't know. But basically, yeah, thank you very much for watching this video. I hope you have a great holiday. If you're going back to work, whatever, enjoy yourselves. Don't drink and derive. And yeah, thank you very much for watching this video. I hope to see you guys again sometime in the future. I really don't know when, but I'll see you. By the way, do you guys like my Supremum shirt? It was made in my real analysis class, and let me actually take it out so you can see a bit more clearly. It was a shirt that we made in real analysis class. The reason it's called Supremum is because, well, I've explained the video, axiom of completeness. At the front it basically says Supremum. At the back it basically has definition of the Supremum and the axiom of completeness printed on there. It's not for sale, I just wanted to show you guys how cool the shirt is. That's all.